I wanted to do a quick video showing you how you would actually compute the curvature of a circle from our fundamental definitions that we had in the previous video. Okay, and I will actually be doing this proof a different way in another video, but let's just go ahead and see what happens here. Okay, so I entitled this curvature of a circle. The first thing I'm going to introduce, I've got u hat, right? So unit vector is a function of theta is going to be this vector, okay? Cosine theta, sine theta. This would be the vector from the origin pointing to what? A point on the unit circle, as you can see, okay? So that's something you ought to remember from basic trigonometry, just written in vector form, right? Now we're going to consider again uniform circular motion that we've talked about previously. So I've got position vectors of points on the unit circle as a function of time t. Cap r we said is what? The radius of the circle. Okay, so that's some positive number. Times what? U hat of omega t. Again, omega is going to be a constant. That's what we're calling the angular speed. Okay, so we could write this out in greater detail. That would be what? Cosine omega t, comma, sine omega t multiplied by r. Okay, just using a slightly different notation. Now, if I go ahead and take the first derivative of the position, we get what? Velocity, right? Okay, and we did this before. First of all, from the chain rule, I'm going to take the derivative of the inner function with respect to t, and that will give me what? An omega, little omega here. That will come out, okay? And then if you actually differentiate this, like we did in the previous example, what you will find this is equivalent to, and I did mention this, is just adding pi over 2 to this, okay? You can always double check and see if I'm not telling a lie here. You'll see that I'm actually not. Okay, so you could think of that as cosine omega t plus pi over 2, comma, sine omega t plus pi over 2, and then use simple sum of angle identities to get the derivative and show that it's equivalent to exactly what you get in our previous example here. Okay, so I'm just doing this quickly, giving you a little work to do here. Okay, now we also mentioned that this thing actually ends up being tangent to our circle at any particular point, so that I'm actually going to write it this way. You remember the unit tangent, okay? So I'm going to write it this way because you notice here this is actually what? A unit vector, of course. There's a hat on it, right? Okay, so that actually corresponds to t hat then, because if I take this vector and divide it by its own magnitude, you see how we get this unit vector here. Since this is a positive constant here, that's a positive scalar. If I actually did that, I would get that t hat is equal to u hat, wouldn't I? Okay, so that's our unit tangent vector from the previous video. Alrighty, so there we go. By the way, when we take the magnitude of this, we were calling that speed. So that's the magnitude of the velocity. And you could see that here because that has a magnitude of 1, since it's a unit vector, and r and omega are positive, that we actually had this. Okay, so this is repeating something we did in the previous video a little more succinctly here. Okay, let's go to acceleration. That's going to be, oh, I guess we could throw this in at the same time. That's ds over dt. Remember, that's the rate of change of arc length with respect to time. Okay, there's not going to particularly help us there, but let's just throw it in. Acceleration is what? The derivative of velocity with respect to time. So that's the second derivative of position with respect to time. Okay, so now I'm actually what? Differentiating this thing. Okay, differentiating this thing. See, when I differentiate the inner function, once again, I get the little omega factor. So I get r omega squared. When I differentiate this thing, just like previously, I will end up adding a pi over 2 to that quantity inside the parentheses. So I would end up with pi over 2 plus pi over 2 is pi, like that. And now if I was to substitute that back in here and compare it to the original, that actually ends up being oppositely directed to the previous one. So I could write this, and it looks like a W. I'm going to go like that, put a negative omega t. That scalar negative could be put on the outside, obviously, but I just want to emphasize something here in a minute. Okay, and we said we could also write it this way because of this formula from that guy right there. We could go that. That's exactly what that's equal to, right? Okay. That's another way of writing it. Okay, so we've seen these things before here. Now I haven't related this yet to curvature, okay, but I'm going to here in a minute. Okay, so let's maybe go something like this now. Let's go back to our definition here. Do you remember dt over ds is our definition of kappa times n hat, where that's what? Principal unit normal, and kappa is the magnitude of this, right? It's the magnitude of that vector, okay? So that's what we're calling curvature, kappa. All righty? Now, let's mention here that t hat of omega t was u hat omega t plus pi over 2. We saw that up here, right? Okay, remember that? Let's go ahead and look at this derivative here. Okay, what I'm going to do is perform a little change, a variable here. Okay, divided by ds over dt. This is involving using the chain rule, right? Okay. Oops, I'm sorry. That's supposed to be a t here. There we go. Better. All right. So we have dt over ds is dt hat over dt, ds over dt. Okay, so I'm dividing those two. So that just follows from the chain rule. Okay. Now, if I actually differentiate this thing, the t hat, with respect to t here, what do we end up getting? Well, we ended up getting, we did this before, we end up getting then negative omega u hat omega t. Okay, so that's what we did up here. Okay, and what is ds over dt? Ds over t is r omega. Okay, so what we get is negative u omega t over r. Okay, so that's now that's dt hat over ds. What was that equal to? That's supposed to be what? Always kappa times n hat. Okay, so that's 1 over r. I'm going to write it this way. Okay, kind of writing it like I did here. I'm going to put the negative u hat on the inside. Okay, I don't care how it's parameterized right now. I'm going to write this statement here. Okay, now you remember kappa is a non-negative number, and if I take what? The magnitude of each side of this, okay, if I say take the magnitude of this side, because that's a unit vector, I would get absolute value of kappa, which is kappa, right? Because kappa is non-negative. And what would I do? What would I get if I took the magnitude on this side? Well, 1 over r is the magnitude of this side, right? Because, again, u hat is a unit vector. So I've, in fact, found that what? The curvature of a circle is a reciprocal of its radius. Kappa equals 1 over r. Okay? Kappa equals 1 over r. Also from this formula, then, you can see here that if I was interested in what n hat was for a circle, that's actually negative of the, what? Direction of the position vector. So it's actually pointing backwards like that. Okay? So you notice that this is independent. This has nothing to do with the position on the circle itself. You notice how there's no parameter here? That's just a constant. Okay, so a circle has constant curvature. Okay, that probably doesn't sound like too much of a surprise to you. Okay, and then what? The unit normal here is pointing, we said the principal unit normal is pointing in the opposite of the direction of the position vector. So let's maybe draw something here. Okay, I should have had a circle drawn here. I'll try. Should have got a compass or something. Okay, all right, well that's supposed to be a circle anyway. All right, so let's say that's just my x-axis. I'll embed this in the xy plane here. Okay, let's say I have a point on this. Okay, so let's say here's our position vector. Okay, so that's r of t. Okay, so this has a magnitude or a length that's cap r. Okay, the unit tangent vector would have a length 1. It would be pointing this way, right, for increasing w, because it's being drawn out like this. If you imagine it being like a point moving here, remember how we assumed that this was greater than 0 and r is greater than 0. Okay, it'd be moving like this then. Where is n pointing? N is pointing this way. It's going to be a unit vector. I'll draw it from the point of tangency here. N is going to be coming in like that. And that's going to be unit vector also. These, of course, are going to be orthogonal, like that. Okay, does that make sense? Alrighty. One last thing I want to throw in here. We could write acceleration this way. Again, this is applying to what? Uniform circular motion. Our acceleration was this. Negative v squared over r u, like that. Okay, as a function of time there. Now we could say this is negative u is actually n, and 1 over r is actually kappa. So we could say kappa v squared times n hat, and that's our acceleration. Okay, this is for an object moving in uniform circular motion. Okay, we could write it this way, or sometimes people even like to write it this way. Remember, v is ds over dt squared. Okay. Or we could write this for uniform circular motion 1 over r, v squared over r n hat. Different ways we could write this thing. These are all true. Okay, and if you look on your formula sheet for some of these formulas involving uniform circular motion or general motion even, these are going to start appearing here. Okay, that's why we looked at these particular types of motion originally. Okay, so don't forget though, what's the curvature of a circle? It's 1 over its radius. It's constant. This is independent of the point on the circle. Okay? Alrighty, I'll let you keep you going for now.